Good afternoon to all of you. First of all, I want to introduce myself. Myself Ankit Acharya, working as an assistant professor in Hasmukh Goswami College of Engineering, and today my content is GTU question paper solution of the subject of vector calculus and linear algebra of June 2014. So up to question number 5A, we already seen this question paper. So let's start with question number 5B. Here is the question number 5B. This question was asked in 5 marks. Verify Cayley-Hamilton theorem for the matrix A, where A is equal to 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2, and hence find A inverse. Here is the solution. Determinant of A minus lambda I. First of all, we have to find the characteristic equation, right? And what is the characteristic equation for any matrix, for any square matrix? That is determinant of A minus lambda I, that is equal to 0. And what first of all we have to do, we have to find first of all characteristic equation, and in that characteristic equation, instead of lambda we have to put A and verify that the statement is correct or not. So first of all we find characteristic equation. This is determinant of A minus lambda I. So that means in the main diagonal entries we have to just add minus lambda, other entries are same. You can see 2 minus lambda, here 2 minus lambda, 2 minus lambda, other entries are same, and determinant of this 3 cross 3, that is equal to 0. So next how we find determinant, that is that you all know, 2 minus lambda, then 2 minus lambda into 2 minus lambda, and then minus 1 plus 1 into minus 1 into 2 minus lambda, so that will become lambda minus 2 and then plus 1, right? So lambda minus 1 and then plus 1 into 1 minus 2 plus lambda, so lambda minus 1, right? Lambda minus 1, that is equal to 0. So when we simplify this step, finally we get lambda cube minus 6 lambda square plus 9 lambda minus 4, that is equal to 0. So definitely the lambda minus 1 is one of the factor, because the coefficient of all the power of lambda, that is equal to 0. You can see 1 plus 9 10, and then minus 6 minus 4. So when we put lambda is equal to 1, this equation definitely it's satisfied. So lambda minus 1 is one of the factor of this equation, and the another second degree polynomial is okay. So our eigenvector here we don't want to find the eigenvalues, otherwise we have to find the value of lambda, right, which is our eigenvalues. But here we want to check that the Cayley-Hamilton theorem satisfied or not. So this is our characteristic equation, lambda cube minus 6 lambda square plus 9 lambda minus 4, this is equal to 0. This is our characteristic equation, and in this characteristic equation we have to put A. So using Cayley-Hamilton theorem we get A cube minus 6A square plus 9A minus 4I, that is equal to 0. That we have to prove, right? So let's try to prove it. A square, first of all we find A square, that means A into A. What is our A? 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. This is also A into A. Now matrix multiplication, in which condition we have to multiply two matrices? There are some conditions, right? So the condition is the number of column of the first matrix, that is equal to the number of row of the second matrix, right? If these two are equal, then definitely we can multiply the matrices, otherwise we cannot. And our new matrix is in size of number of row of the first matrix into number of column of the second matrix. So and how we multiply? We pick up the first row and multiply with each column. So 2 into 2 4 plus 1 plus 1, so 6. Then first row multiply with the second column of the second matrix. So minus 2, minus 2, minus 4, minus 1, so minus 5. Okay, and then multiply with the third column. So you can see 2 into 1 2, then plus 1 3, then plus 2 5. Then second row, multiply with each column. So you get minus 2, minus 2, minus 4, and then minus 1, so minus 5. Similarly you will get 6 and minus 5, and then 5 minus 5 6. So a square is this one. Now a cube, a square into a, that is 6 minus 5 5, minus 5 6 minus 5, 5 minus 5 6, into 2 minus 1 1, minus 1 2 minus 1, 1 minus 1 2, that is equal to, again we can multiply 3 cross 3 matrix. You can see both the matrices are in size of 3 cross 3, so definitely we can multiply this two matrices, and that is 22 minus 22 minus 21 minus 21 22 minus 21 21 minus 21 22. Okay, so let's see this equation is satisfied or not. We have to put all the values. Now we have a cube, a square, a and identity matrix. So put all the values in this equation. So we get a cube minus 6a square plus 9a minus 4i, that is equal to, you can see we put the values of a cube, then a square, and a, and then identity matrix, and then add all the matrices. So finally we get the 0 matrix, right? 22 minus 36. Just check one element, just one element. So this is the first element, so let's check is it correct or not, and other elements you can definitely easily one by one you can check it. 22 minus 36, then plus 18, so 22 plus 18, that is 40, and this is minus 36 minus 4, so again 40, so 40 minus 40 you will get 0. Okay, similarly you can check one by one each and every element, then addition of this matrices, finally you will get the 0 matrix. So the Cayley-Hamilton theorem is definitely satisfied for the particular this example. And using Cayley-Hamilton theorem we also want to find A inverse. Okay, so this is our equation, a cube minus 6a square plus 9a minus 4i, that is equal to 0. We get 0 means 0 matrix. Now we are multiplying on both the side with A inverse. So A inverse into a cube minus 6a square plus 9a minus 4i, that is equal to 0 into A inverse, so you will get 0 matrix. A square minus 6a plus 9i minus 4a inverse, that is equal to 0. So 4a inverse, that is equal to a square minus 6a plus 9i, a square. So this is the value of a square. 6 minus 5 5, minus 5 6 minus 5 5 minus 5 6, minus 6 into, this is a value of a, 2 minus 1 1, minus 1 2 minus 1 1 minus 1 2, plus 9 into 1 0 0 0 1 0 0 0 1. So 6 minus 12 plus 9, so 9 plus 6 15 minus 12, you will get 3. Then you can see minus 5 plus 6, that is 1 plus 0, so you will get 1. So finally 4a inverse, you will get this matrix 3 1 minus 1, the first row, the second row is 1 3 1, and the third row is minus 1 1 3. Now if you want to find the value of A inverse, so that is equal to, A inverse is 1 by 4 into 3 1 minus 1 1 3 1 minus 1 1 3. So here is our answer, A inverse. Using Cayley-Hamilton theorem we can easily find the value of A inverse. So this question was complete. Now next question, question 5c. Find the canonical form of the quadratic form Q, capital Q. Q is equal to 2x1 square plus 3x2 square plus 2x3 square plus 2x1 x3 using orthogonal transformation, and also find index, rank and signature of the quadratic form. So here is a solution where capital X is x1 x2 x3 transfers, capital Q is equal to x1 x2 x3, and how we find this matrix, you can see the coefficient of x1 square, x2 square and x3 square, that is 2, then 3 and 2 respectively, right? So our main principal diagonal elements, we add 2, 3, 2. Okay, you can see the coefficient of x1 square, x2 square and x3 square, that is 2, 3, 2. So our main principal diagonal elements in this matrix are 2, 3, 2. Then coefficient of x1, x2, that is 2, and in matrix this element, this coefficient will be divided by 2, so you will get 1. So 1, 1 we separate in this position 1. So this value is for x1 x3 and this is for x3 x1, so that's why put 1, 1, and the coefficient of x1 x2 and x2 x3 both are 0, so that's why other elements are 0. Okay, so using this method we can find this matrix. So our A is equal to, now you can understand, this is our matrix. A is 2, 0, 1, 0, 3, 0 and 1, 0, 2. Now also we want to find the eigenvalues of this matrix A. So again we use the characteristic equation which we use before previous example, in previous example. So determinant of A minus lambda I, that is equal to 0. So 2 minus lambda, in main principal diagonal elements we add 2 minus lambda, 3 minus lambda, 2 minus lambda, other elements are same. Now simplify this determinant, the value of this determinant, that is 2 minus lambda into 3 minus lambda into 2 minus lambda, right, minus 0, this is also 0, plus 1 into lambda minus 3, that is equal to 0. So lambda minus 3 will be common. Finally in the bracket you will get 4 minus 4 lambda plus lambda square minus 1, that is equal to 0. So finally you will get lambda minus 3 into lambda minus 1, that is equal to 0. So how many eigenvalues we have? 1 and 3, 3. So 1 occur in one time and 3 occur in 2 times. So if you want to find algebraic multiplicity of an eigenvalue, you can say that algebraic multiplicity of 1 is 1 and the geometric multiplicity of and algebraic multiplicity of 3 is 2. Okay, because you know that the algebraic multiplicity is depending upon how many times our eigenvalue occur, right? So 1 is an eigenvalue occurring only one time, so that's why algebraic multiplicity of 1 is 1, and 3 is an eigenvalue occurring 2 times, so algebraic multiplicity of 3 is 2. Okay, here that is not our question, but if we suppose ask in algebraic if we suppose ask in this question that algebraic multiplicity, find each and for each and every eigenvalue, then we can find using this method. Okay, so let's see how we find eigenvector corresponding to eigenvalues. For lambda is equal to 1, put lambda is equal to 1 in this matrix, in this determinant. So finally you will get 1 0 1, 0 2 0 and 1 0 1. Okay, so 1 0 1, 0 2 0, 1 0 1, x1 x2 x3, that is equal to 0 0 0. So you will get two equations, x1 plus x3 is equal to 0 and second is 2x2 is equal to 0, right? You can see first and third row are same. So in which column we don't have any leading entry? Third column. So that's why we are taking x3 is equal to k, and corresponding to x3 is equal to k, we get the value of x1, that is x1 is minus k, x2 is 0. So our eigenvector corresponding to lambda is equal to 1 is minus 1, 0, 1. Now also we want to find eigenvector corresponding to lambda is equal to 3. So put lambda is equal to 3 in the previous step. You can see in lambda is equal to 3, when we put in this equation we get minus 1, 0, 1, 0, 0, 0 and 1, 0, minus 1. Okay, so for lambda is equal to 3 we get this matrix minus 1, 0, 1, 0, 0, 0, 1, 0, minus 1, x1, x2, x3, that is equal to 0, 0, 0. So x1 minus x3, finally we get x1 minus x3 is equal to 0. So take x3 is equal to k. So x1 is equal to k, and let x2 is also k. So our eigenvector corresponding to lambda is equal to 3 is 1, 1, 1. Now for another lambda is equal to 3, choose x2 is equal to minus 2k. So our eigenvector x3 is equal to 1, minus 2, 1. Okay, so you can see the dot product of each and every eigenvector, any two eigenvector, that is equal to 0. The x1 x2 is 0, x2 x3 is also 0, and x1 x3 or x3 x1, that is also 0. You can see what is our x1 x2 x3. This is our x1 minus 1, 0, 1, and this is x2 1, 1, 1. So dot product of x1 x2, that is equal to minus 1 into 1, that is minus 1, plus 0 into 1, that is 0, plus 1 into 1, that is 1. So minus 1 plus 1, you will get 0. Similarly when we find the x2 into x3, so that is 1, 1,